Hello, my name is Brandon Jones, and I'm doing my video walkthrough for my TicTacToe project for game theory. Okay, so let's open up the game in Unity. We have the main menu, we have the play button, options button, and quit button. The quit button doesn't work in debug mode for Unity because it uses application.quit. So let's just go right into the game. We'll go back into the options state after we've run it once. So go into the game, and it's a basic player versus computer mode. So I put down a tic-tac-toe piece right here. He puts down one using the minimax algorithm. I'll put one down here. He'll go right there. I block him here. He'll put one there. Put one there. He blocks there, and it's a draw. So we go into, so it comes out as a draw. There's a button that sits flat across the screen, very elegantly. So we click this, we go into this. The credits menu just has my name and the date, as well as the button to go back to the main menu. So go back to the main menu. As you can see in the options menu, we have an easy and hard mode for that easy AI. The easy AI is just a greedy algorithm, and the hard AI is the minimax algorithm that goes all the way through. We have our computer versus computer, player versus computer, and player versus player mode. So if I go into player versus player mode, we have me putting X's and O's all over the place. Player 1 wins. Hooray. Okay, so back into the main menu, we say computer versus computer. AI is on hard mode. So we play, and they'll go back and forth. I have the bots set to wait a second in between each of their turns. So there they go, and then it's a draw, as it will always be in the minimax algorithm. Okay, so I have for my extra content, and technically my code could go into any number of board sizes, but I have it go up to 8 for now because 8's a pretty big number. It seemed big enough. Any more than that is just kind of really overkill. So let's just go up to 8. So we got 8. I have the computer versus me. So we're gonna do a very boring match of 8 by 8 tic-tac-toe. As the board gets bigger, I'm doing a less and less sophisticated AI tree, or AI algorithm. So it's right now, the bigger it gets, the more of a greedy search it is. So he will eventually win right there. If I tried to actually play, no one would have won, and it would have lasted forever. So we can do a somewhat more interesting game of 4v4 up against a hard AI. Main menu, play game. So I put one here, he puts one there, I'll put one there. He'll block me probably, yes. I'll put one there. He wants to go for the diagonal, I'll block him there. Now he wants to go for that, I'll block him there too, and now there's no hope of anyone winning. So we'll just run this out to a draw. Draw. Okay, lastly I'll show you a 5v5. Just to show that it's not fake. There we go, 5v5. So bam, bam, bam. Let him win, and then I'll do it again, but with the computers going against each other. So he did something a little funny there because he was using a less sophisticated AI. So let's go 4v4 mode, bam. So AIs are going against each other in 4v4 mode. Of course, it is still using a mainly minimax. It has a depth of, I believe, 4 at the 4v4 limit. So it's not a full minimax, but it's enough so that they know what they're doing. Okay, and lastly, I'll do computer versus with the AI easy. So they are easy, so it's a greedy algorithm, so they'll just go for whatever is best for them. So right there at the end you saw that the X's, rather than blocking that guy and looking at what he'd do next, he just said, oh, well, I'll get a pretty good score if I put it here instead versus not trying to block him out. Okay, so now we can get into the code. Let's close this down, bring up the code. So main menu, simple. I have a button style to increase the font size. I have buttons for play, options, and quit. Application.quit for quit, and then it just loads up the scenes of the other options. I have it dynamically based on width and height of the screen. So in options, we have a similar thing. We have buttons for controlling things. I have a toggle button for, or I guess it's just a regular button for the easy and hard AI toggle right there. I've got all these horribly disgusting looking begin horizontal and flexible spaces to try and center them across the screen with GUI layout. It's not very beautiful, but it got the job done for the most part. In actual game, if I was writing an actual game, I would probably not use these, mainly because they're ugly and hard to place. I hate them. I would probably, with the Unity 2D, use sprites and on clicks do things for buttons. That seems a lot prettier to me as far as coding goes than this. Okay, so moving forward, we have the credits, which is simply just outputting my name and the date, and then it has a button for main menu. So, moving forward, into the actual zone logic. The zone logic is the actual tiles on the board. So the only thing that this class does is handle the aesthetic, what the tile looks like, whether there's an X and O or it's blank, which is done right here. And it handles player input. So because I'm handling both touch and mouse input, I have on mouse down and I have on touch in the update, both calling this function for touch input for the player. So the player would say make player move to the board logic, which it gets during its initialize. The board logic is sent over, and the board logic would then do its crazy stuff in order to make the logic happen on the other side. So what it does is it make player move comes in here. It checks to make sure it isn't a computer versus computer game. Checks to make sure that if it is a player versus computer, it is the player's turn. Otherwise, touch input works all the time because it's one of the player's turns. And going forward, we have the player turn the make game move, which will set the game board's zone state. So this zone, the tile, it sets its zone state, and upon doing so, it changes the sprite that is associated with that object. So it makes it an X and O or blank based on what it's being set to. So after that happens, the actual after the aesthetic things happen with the game board on the actual game board side, it sets its game state to make a move, and we'll go into that later. So after that happens, we resolve the turn, we get the next player with the current game state in the player turn, and if get next player, if the game is over, it will return 0 for the player turn, and it will end the game essentially. We'll go into and then the GUI handles the rest of it. We'll go into that in a little bit as well. If the game is a computer versus computer game, or it's a player versus computer, and it is the computer's turn, then we will start up the AI logic. So I have it as a coroutine so I could do a yield return, which is a simple way to wait for a second so that when we do a computer versus computer game, we can kind of see it play out rather than it instantly finishing. So we have that going. If it is in easy mode, the depth, so the number of times we're running this algorithm, or how far deep we're going into the minimax tree, is set to 0, so it becomes an easy or a greedy algorithm. Otherwise, if it's a regular tic-tac-toe game, so just a 3v3, then we just do a minimax. We go all the way through the tree. Otherwise, we set the depth based on how big the board is, because we don't want to do a minimax algorithm for an 8x8 board. That would be it wouldn't be very efficient. It would take a very long time. So we're doing a depth so that we have some kind of sane calculations during those modes. So we have the actual AI makes their move, and through this is the minimax algorithm essentially. So we have the minimax go through each available move. It checks the new state. It makes the move it makes the current move, and then it checks to make sure that the depth is not. It checks to either make sure that the depth is irrelevant or whether or not it is on the depth, as well as whether or not the game is ended. So if the game's ended, it stops. If otherwise, it keeps going. It goes all the way through the tree. Passes in death -1, so it'll keep going. So beforehand, when the death is in a normal case, like if we want to use the minimax, I just have it as a depth of -1, so it will never be equal to 0, and it will just keep on going downwards, and so it'll finish until the very end. So if the best move is not equal to null and the move is better, this is better function that depends on the player turn. It'll return the appropriate whether or not it is better. Okay, so moving forward, we have the actual make move, the make game move. Oh, sorry, the make move function within the game state. So the game state is actually the one doing all the evaluation of the moves and setting the actual logic side of the game state. So we have right here, the game makes a move. That's what's being called through the minimax algorithm, and it sets the game board to the player turn that's passed in. So it'll be +1 or -1 depending on the player turn, which determines the value of the board at the time. Okay, so then it evaluates the game state. So it goes through. I'm doing a little bit weird in comparison to the example. Evaluate game state gets the values of the rows and columns as well as the values of the diagonals, and then outputs both. So I'm going through each set of possibilities. So I'm looping through the entire board, and I'm saying I know that all of the y values will go through on this. So it goes down, down, and down. So I know if these y0 through the board dimension or go down it'll go through that whole row or that whole column essentially. So I'm adding up all those values, and if those values are equal to if that value squared, because I don't want to have to deal with the negative or positive issue, is equal to the board dimension squared, then the game is won. And that's how I can do it with an unlimited number of board dimensions, because regardless of how many you want in a row, so if the board is at 1000 by 1000, it will check to make sure that this value is 1000 squared versus you are 1000 squared. And the only way to win is if all of those values come out correctly. So if one of these values is blank and the other two are filled, then that would be 1 + 1 = 2. 2 squared is 4. If 4 is not equal to 9 squared, so it wouldn't end the game. And I do this same general principle for the x values as well. I'm capturing those, and I'm doing the same logic right here. Now, in order to get my actual game state value, I'm getting this value cubed, because I wanted it to be I wanted to get a value that increased as you got pairs, as you got matches. But I couldn't do it squared because that would eliminate our difference in positive and negative values, which is how we're determining which player is winning, how we can tell the pieces apart. So if it's 3, so if you have a full match, it's 3 times 3 is 9, times 3 is 27, and that is a lot bigger score than if I were just to multiply them by a value per time. It doesn't increase exponentially. So same thing if we had 2 matches, that's 1 plus 1 is 2, 1 plus 1 is 2, and then 2 times 2 times 2 is 8. 8 versus 27 is a pretty big difference, and it got me the proper heuristic that I was looking for. So we're going down. Diagonals do the same thing, but they're a little bit easier to find because there are only 2 of them versus the 3 rows and the 3 columns, and they're pretty static. So I'm doing this to get the same kind of thing. It's the same kind of logic behind the values. So I get both of those together to check. Oh, and also if it is a victory on one side or the other, I'm capturing that value right here. Okay, so I'm returning this game state. Board logic is going to pick it up if it does do that, if it is a victory case, and then break out, and then it's going to make its move based off of that. So it's going to call make game move, which is right up here, and make the move and resolve the turn, so pass the turn to the next player. And it continues like that until the game is over. So as far as options go, I forgot to talk about that. Options are saving out to a handy Unity class called Player Preferences. So if we go to that, when the credit scene ends, so when this object's destroyed, it sets these integers based on this key sent in and these values that are set in option state, and then they're picked up in game state, board logic, and they're picked up in load preferences at the start of the game, and then it sets all these things and then deletes them on when the game object is destroyed. Okay. And that is about it for the actual game. We'll set this up to one higher number, CPU, go. Okay, so my impressions of this assignment, at first I thought it was going to be really easy because I'd already handled a minimax algorithm in the past. I'd already done it in the Game Development Bachelor's program for Full Sail. But as I went through it, it was a little bit more difficult than I remember it being. And I debugged the same problem for 4 hours. It was very simple until I finally finished it. But other than that, I thought that this was really valuable. It got me a good first look into Unity 2D, which I'd not messed with Unity 2D before. It seems really useful, and I really enjoyed this assignment. That's it.